So today we'll start a new topic, which is basically optical transmitters. Right, and basically for optical communication, there are sort of two main types of sources used, which are both sort of based on semiconductor technology, specifically three types of semiconductor technology, as you'll see. So basically LEDs and lasers, right? So light emitting diodes are sort of broadband and incoherent, right? So whereas lasers are narrow line width, as you know, coherent sources with well-defined, so you could have very precise frequency and phase. So LEDs typically, I mean, they were used in sort of the early generation optical communication systems. And nowadays also they're used in some places for very short links, like within data servers, or where basically your link length is, let's say, below a kilometer or so. Because as we saw that with these broadband incoherent sources, like dispersion is a big issue, right? And so for long haul links, typically mostly we use nowadays single frequency lasers with very narrow line widths, less than a megahertz. Right, so basically, typically they're made of semiconductor materials. So I guess a lot of this would be sort of refresher for you guys from maybe the photonics devices course that you did, right, last semester. So we try to maybe go through some of this material a bit quickly, because a lot of this you should probably be knowing already. Right, so basically there are a lot of advantages to making these light sources out of these semiconductor materials, right? First is, of course, we get the right wavelength range that corresponds to the minimum loss window for silicon optical fibers, right, that we saw. So using this, you can make sources like easily anywhere between 1.2 and 1.7 microns, right? We saw typically the telecommunication bands, the optical bands slide between like 1.25 to 1.65 micron, right? So we can cover the entire range of wavelengths with this technology. Okay, so the other is that they can be made very compact, right? So small form factors, typically the sizes we are talking about are tens or hundreds of microns in size, so it's a small chip, right? And so the mode emitted by these devices, so the light coming out of the device is typically matched to the mode size in the optical fiber, right? Matched to, for example, SMF. Okay, so we can easily couple the light coming out directly into optical fiber, and many of these devices actually come already what is known as pigtailed to a fiber already, right? So if you can buy these things off the market, so typically like there'll be some what is known as a butterfly package, so you can put them on a holder which has temperature control and current control, everything, and then there's a fiber already like sort of attached to this and coming out. Okay, so the light directly comes out into the fiber. And of course, they are current driven, so right, so that's easy. You don't need, for example, optically pumped sources or lasers. You need like some external another optical source, or sometimes some lasers you need like some very high voltage to pump them. But here we just simply need some. We'll see like the currents we are talking about are like few milliamps to maybe hundreds of milliamps, right? And the voltages we are applying are a few volts. So very easy to integrate with sort of the electronic infrastructure that we have. The current driven and can also be directly current modulated. Right, so directly we can transfer the electronic data onto the optical form by direct modulation of the current, for example. So that's very convenient, and we can do this up to, let's say, like gigahertz frequencies. If you want to go beyond that to tens of gigabit per second or beyond, then we typically use external electro-optic modulators. Okay, so basically, of course, like this development of the global optical communication networks heavily depended on the invention of these semiconductor-based light sources, along with the development of the optical fiber. Right? So basically, the basic mechanism of light emission in these devices is basically you inject current into the device, right? So basically, you know that semiconductor materials have a valence band and a conduction band with some band gap. Right? So typically, by current injection, what we do is we sort of send or populate the conduction band with some electrons here, and also equivalently populate the valence band with some holes. Right, so you know current is carried in a semiconductor via these charge carriers, which are electrons and holes. Right? So basically, through current, we inject these charge carriers, right? And then basically, once the charge carriers are in the material, then basically they can recombine. Right? An electron can go down from the conduction band to the valence band and annihilate a hole, and in the process emit a photon. Right. So, and you can see, so the energy of the photon will roughly be the band gap energy. So we can control the wavelength of emission by controlling the band gap. Okay. And we see, we'll see that basically using these 3-5 semiconductors. So the specific semiconductors which are used are combinations of materials from group 3 and 5. Okay. So the standard semiconductors that you know of from group 4, like for example silicon or germanium, cannot be used, as you know, for light emission because the band gap is indirect. Right? So basically, the minimum of the conduction band and the maximum of the valence band does not occur at the same momentum. Right? So typically, this is what is known as the EK diagram. Right? So this is the energy of the electron, and this is the wave vector or the momentum. Right. So basically, for light emission, what we want is that this minimum of the conduction band and the maximum of the valence band have at the same K value. Right. So basically, there is no momentum exchanged by in this recombination, and basically you just emit a photon with the corresponding energy. Right. So here, basically, if the electron has to relax, then basically you also need to account for this change in momentum. Right. So that typically is not efficient. We need like some other, right, phonon assisted recombination mechanism. So the light emission in these materials is very poor or next to negligible. So as you know that, yeah, so this is sort of like a long-standing goal that if we can make some light sources in silicon itself, because of the well-developed nanofabrication technology from electronics that we have for silicon, we can also make nice optical waveguides and other photonic devices in silicon. But the main thing missing is a light source. So anyway, so basically we use combinations of materials from group 3 and 5, right? So for example, gallium arsenide or indium phosphide, right? And we add some other materials to this in different mole fractions, for example, aluminum to gallium arsenide, or gallium to indium phosphide, or even arsenic, right? And by the concentration of these different atoms here, we can control, for example, the band gap, right? And we can control the emission wavelength, right, over this entire telecom range, right? So we can grow these materials very nicely in a crystalline manner, okay, without any defects, and also control the band gap and the emission wavelength very precisely. So, okay, so and typically these devices are based on what are known as PN junctions, right? So basically, you have some. So you know what a P-type material and N-type material is. P-type is when we have doped the material with a certain atom such that there are more holes. N-type such that there are more electrons. And when you sandwich these two types of material together, you get what is known as a depletion region or PN junction. Right? And basically, when you forward bias this PN junction, you can drive current through the device, inject charge carriers, and have recombinations. So basically, light sources are forward biased PN junctions, right? And later on in the course, we'll see that when we look at optical receivers or photodetectors, they are basically sort of the same type of device, but operated in the reverse biased region. So when you operate these PN junctions in the reverse biased region, the opposite effect happens. You can detect photons. So an incoming photon can create electron hole pairs, and then you can separate them and generate a current. Okay, so first, anyway, for now we discuss transmitters or light sources. So quickly, maybe just some review of basic semiconductor physics that again you probably are familiar with. Right. So typically, yeah. So you have this conduction band and valence band, right? Separated by the band gap, and then you have something known as this Fermi level, right? Which is basically determined from sort of the concentration of the charge carriers in your material, right? And where this Fermi level lies with respect to the conduction of valence band tells you, like, for example, if you have more electrons or more holes, etc. So you know, for example, in an intrinsic semiconductor, this lies exactly halfway, right? So for an intrinsic or undoped semiconductor, the Fermi level is right in between, right? And basically, so if you look at, for example, how many energy levels are available to be occupied, right? So there is some density of states in the conduction and valence band, right? So for example, in the conduction band here, this density of states as a function of energy, right? So y-axis is energy. Let's say, so x-axis is some position within the material, right? So this goes as the square root of the energy difference from the conduction band, right? So those as basically more and more states are available for electrons to occupy as you go away from the conduction band edge. Right? Similarly, for holes here, there is a density of states which is dependent on the square root of the energy difference. Right, so this is coming from fundamental solid state physics. So when you solve for the energy levels of the solid state medium where all the atoms are bonded to each other, right? And then you find solve for the energy levels depending on the atomic potentials, etc. Right? So you get the number of states available to be occupied, goes like that, square root of the energy, right? And then along with the density of states, you know there is something known as so if you want to find out how many charge carriers are available either in the conduction band or valence band, then basically first we take the number of states which are available to be occupied, and then we multiply it by the probability of a state to be occupied, right? And that goes as the Fermi-Dirac distribution, right? So there is this Fermi-Dirac distribution which tells me what is the probability that a particular energy level E will be occupied by the electron, right? And for holes is basically hole is an absence of an electron, right? So the probability that a hole occupies an energy level here is basically the probability that an electron is absent. So it's 1 minus the probability that the electron is present, right? And so basically when we multiply this number of states by the probability, so you can see that we'll get some distribution here like this, right? So it will peak just close to the conduction band and then fall away again. So that will give me the charge or carrier concentration, the electron concentration in the conduction band. Similarly, when I multiply these two, I'll get here. So this will be P, the number of holes, right? As a function of energy, and this will be the number of electrons as a function of energy. Okay, so the total number of electrons I can find out by integrating this carrier concentration as a function of energy, right, over the energy coordinate. So I go from EC to plus infinity. So this is the density of states multiplied by the occupation probability integrated over energy. Right? That's the total number of electrons in my medium. So this Fermi-Dirac distribution, recall, has a functional form like this. Right? So Kb, Boltzmann constant, T is temperature. So okay, so again, it depends on the difference of the energy level from the Fermi level. So you can see at the Fermi level, the occupation probability is half, right? And as you go higher than the Fermi level, then your occupation probability decreases, right? So it's something like the electrons are filling up energy levels starting from the lowest energy level, right? And as the energy level goes higher and higher, the occupation probability is going down. And similarly, we can find the number of holes. So by integrating from the negative energy to EV, okay. So the probability of finding a hole is absence of electrons, 1 minus. Okay, so again for an intrinsic semiconductor, so you can see that if I change the position of this Fermi level, right, this distribution will shift up and down, right, and that you can see this will change this charge concentration. So if EF shifts up, right, so this curve will shift up, so I'll have higher probability here of being occupied, so I'll get more electrons and less holes. Similarly, if EF shifts down towards the valence band, then I'll get more holes and less electrons. Right, so that's doping. But if you take an intrinsic semiconductor, undoped, then EF lies in the middle, so basically right? And so from here you can see that basically N will be equal to P, right? Because now this is symmetric about the middle. So N so in an undoped semiconductor, both we have an equal number of electrons and holes, which is given by the intrinsic concentration, which just basically depends on the temperature and some material properties. Like the effective mass of the electron and hole. Right, so it depends on temperature here. So typically it scales with T to the 3/2 and other constants, Boltzmann constant, Planck constant, and here we have the effective mass of the electron and effective mass. So you know that the mass, that the inertia that the electron or hole feels in a semiconductor is different from the bare mass of the electron. Right? So here we have the effective mass. Okay, so again, as an example, if we take typically T as room temperature, then kBT comes out to be about 26 milli electron volt. So again, in this field, basically energy is typically measured in electron volts, right? 1 electron volt is basically 1.6 times 10 to the minus 19 joules, right? Basically, the energy gained by an electron if it's accelerated through 1 volt. So it's good to keep this conversion in mind, right? So room temperature kBT, the thermal energy corresponds to 26 MeV. So for example, if we take silicon, the band gap is about 1.12 electron volt. So if you calculate from here, the intrinsic concentration comes out to be about 10 to the 10 per centimeter cube. If we take a 3,5 material like gallium arsenide, so for gallium arsenide, this band gap is 1.42 electron volt, and so to calculate the intrinsic concentration, that comes out to be 10 to the 6 range. Okay, and mainly, for example, you can see that it's coming from I missed out a factor here, right? So it's this constant times. So of course it has to depend on band gap also, right? The intrinsic concentration depends on the band gap. So I forgot to mention that here. So this constant is some N naught. Okay, and Ni, the intrinsic concentration is this N naught times exponential of minus. Okay, so the band gap divided by the thermal energy exponent. Yeah, as pointed out by the student here. So this exponential factor is right. So this N naught depends on the effective masses and the temperature, but the the scaling with band gap comes from this factor. Right, so you can see it's an exponential dependence on band gap. So if band gap increases, so here we go from 1.1 to 1.4, then the intrinsic concentration drops drastically, right, by orders of magnitude because of this exponential dependence. Okay, so yeah, so another thing to keep in mind, so basically the carriers are spread over sort of an energy scale which is here roughly kBt. Right, so above and below the conduction band, there is a spread of energies of roughly the thermal energy over which the carriers are distributed. So it's not just one, they're not at some one particular energy level or yeah, there's some small spread here. Okay. That's this factor here. Okay, so you know that of course we rarely use intrinsic semiconductors by themselves, right? To make some useful devices, we typically have to dope them, right? To make them like p-type or n-type, depending on electron concentration. So briefly, let's just revise the concept of doping. Right, so n-type and p-type. This has excess electrons now. P-type has excess holes. Right, so for n-type, what we do is we dope the material with an atom which has. So this is EV, EC, right? We dope the material with some atom which has a energy level corresponding to its valence electron, which is close to the conduction band. Okay, so this is some donor energy level of the atom we are doping, right? And basically, it can easily lose electrons to the bulk medium into the conduction band, right? So if this is very small here, let's say close to the thermal energy, right? If this is of the order or around the thermal energy, then basically just the thermal energy can excite an electron from this donor level to the conduction. Okay. So basically, what that does is that shifts the Fermi level from the middle to close to the conduction band, right? So basically, because of this mechanism, you can see now basically more electrons can occupy my conduction band, right? So effectively, it sort of shifted the probability distribution upwards. Okay. So now basically this probability distribution extends a lot more into the conduction band, or the values are much higher here, right? So when we multiply by the density of state, then we get a much bigger number here, right? So basically, this number goes up a lot. Again, because this factor now is much smaller, EF goes much closer to EC, and since this is the exponent, right, this becomes much larger. And then correspondingly, when we do 1 minus this, you can see that there is hardly any probability of holes occupying here. So this very, very small or negligible number of holes. Okay, so yeah, so this is n-type doping, right? And p-type, you know, is basically if you dope with an atom which has an energy level close to the valence band, and it's one lower in valency, so it can accept an electron, right? Easily from the valence band. So you can see now easily it creates more holes here. So it's like basically shifting the EF down towards the so if you look at the holes, now there are more holes and hardly any electrons because this distribution has decayed to 0 by then. Right, so this is the perfect. Okay, so for example, for silicon, you know that if you dope with phosphorus, so it has one extra electron, then that's n-type doping. If you dope with boron, which has one less electron, then that's p-type doping. Right? So similarly, we can do for 3,5 materials also. Okay, so typical doping values. Okay, so now we've changed the concentrations of the electrons and holes. So for an intrinsic semiconductor, they are equal, right? So now by doping, we can change them, but they obey what is known as this mass action law. That basically, if you take the product of the concentration of the electrons and holes, you will get square of this intrinsic concentration. So for the intrinsic semiconductor, both of these individually are equal to Ni. With doping, we can increase one and decrease the other, but the product is conserved. Okay, that's again coming fundamentally from these integrals here. Right? So even if you shift the level of EF, this product is independent of that. Okay, so this is known as the law of mass action. Okay, so and basically for n-type, the number of electrons roughly becomes equal to the doping, the number of dopant atoms or the concentration of the dopant atoms that we do. You can almost imagine that each dopant atom is releasing one electron here. Okay, so basically the number of electrons here is basically roughly just the dopant concentration. Okay, and so P will be, you can see, right, and for p-type, P will be like roughly the, again, concentration of the dopant, which is the acceptor concentration, and then N. Okay, so of course here, so typically the doping concentrations we are talking about, either B or A, is can range anywhere from 10 to the 16 to 10 to the 20 per centimeter cube. Right? So you can see that the intrinsic concentration was like 10 to the 6 to 10 to the 10 in this range. Here we are talking about many orders of magnitude higher than that. Right? So this is much greater than Ni. So you can see from here then, so if Nd is much greater than Ni, then N will be much greater than P. And again, if Na is much greater than Ni, then P will be much greater. Right? And so basically, at these doping levels, we can say that there's only one type of carrier present. Right? In N-type, it's electrons, in P-type, it's holes. Okay, and then basically you know that sort of the basic semiconductor device that one can make using these P and N-type devices is a PN junction. Right? So we just join a P-type material with an N-type material. So a PN junction is like the most basic semiconductor device using which all other electronic and also optoelectronic devices are made. So now again, let's briefly review p-n junctions. Right, so yeah, basically what you do is take a p-type material and then join it with an n-type material. Of course, how you practically make a device out of it is basically you grow the material epitaxy up to some point, you dope it with some p-type material, and then grow the other some more material and then dope it with n-type. Or if you do it laterally, then you mask one section of the material and then dope p-type, then mask the other section of the material and then dope n-type. So it's not that you take a piece of p-type and piece of n-type and physically join them. Usually this piece of material is grown together, so it's one piece of material with just different types of doping in region. Anyway, so you can see in the p-type material, of course, we have excess holes. In n-type material, we have excess electrons, and right at the interface, you can imagine that some electrons can diffuse into the p region because there is a dearth of electrons here, excess electrons here. So just by diffusion, some of them can come over to this side, right? And when they come over to this side, they see a lot of holes. So they can sort of recombine with the holes and basically decrease the number of holes here, right? Similarly, holes can diffuse into the end region and then combine with the electrons there, and then again deplete the electron concentration there, right? So basically what happens is that there is a depletion region created here, right, which is basically a region which is free of charge carriers, right? So there are a lot of holes here, there are a lot of electrons here, but right at around the interface, there is a region where basically the charges have cancelled each other out, and it's a charge-free region called the depletion region. Alright, so now if we look at the energy level diagram of this type of material now, so this is just, we are not applying any external voltage yet, okay? So basically the Fermi level has to be at the same place everywhere along the material. Okay, so on this side it's p-type, so that means EF is close to, or it can also go into the valence band depending on the level of doping. Okay, and here it's n-type, so okay, so this is EC, this is EV. So you can see here, so I've shown a degenerate doping case where basically the doping is so high that EF goes into the valence band. And similarly here, the doping is so high that EF goes into the conduction band. Anyway, so there are a lot of holes here, you can see, right? Because the Fermi level is now into the valence band. Again, recall this picture, right? And similarly here now there are a lot of electrons because the Fermi level is into the conduction band. And in the middle here, there is some band bending happening. And basically, roughly, you can see that the Fermi level is in the middle of the band gap, in this region middle here. So in the depletion region, sort of it's almost like an intrinsic material with no charge carrier, or very few charge carriers compared to the charge carriers. Okay, and basically this band bending, right? So this is basically, you can see the energy is varying with position. X, right? This is energy. So energy varying with position, you know, is like a force, right? And force for charge carriers is like an electric field, right? So anytime you see some band bending happening in some solid state material, that means that there is some electric field in that region that the charge carriers are experiencing. Okay, and so basically, so in the depletion region there is a large electric field that the charge carriers are experiencing. Okay. So, in other words, you can see that there is some barrier here, right? If the electrons want to go over from the n side to the p side, then there is a huge barrier here, right? Effectively, it's like an electric field which is imposing a force in the backward direction. Similarly for the holes. Okay, so of course, because holes and electrons are oppositely charged, the force on them will also be in opposite directions. Okay, so typically the width of this depletion region is a few microns, let's say 1 and 10 microns, depending on the doping level and the specific semiconductor used, but typically it's in the few micron range. Right, so basically, yeah, so if we take this PN junction and just at sort of steady state without any voltage being applied, you can see that there is this electric field set up which acts sort of as a barrier for flow of the charge carriers. So, of course, there is no current flowing or okay. So now we can apply external voltages to this PN junction, right? So we can apply a potential difference between the P and N side, and depending on the sign and the value of this potential, basically we can overcome this band bending, right? And so if we apply voltage in a particular direction, so what is known as forward bias, so we apply positive voltage to P and negative voltage to N, then basically we compensate for this band bending and we sort of flatten the band more, and you can see that reduces the barrier height, so current can easily flow. Whereas the other case, reverse bias, we make this even bigger, right? And so you can see that that means that even you suppress the current flow even more. But for optical transmitters, we use PN junctions in the forward bias region, right? So basically a forward positive voltage to P, negative voltage to N. Right, so if you look at a forward biased PN junction, then now when we apply a potential difference between the P and N sides, basically that means that the Fermi level on both sides now are not equivalent, but there is some potential difference, right? Which is basically the difference in the Fermi levels between the two sides. Okay. So basically, if you do a forward bias, so positive voltage here, negative voltage here, then basically this sort of shifts up and this shifts down. So basically, if you look at the Fermi level now, right? So there is a difference between the P and N sides, which is basically the amount of voltage I apply. Right? So the electronic charge times the voltage I apply is the difference in the energy. That's the energy level. Right? So basically, if I do this, if basically this shifts up by V, you can see that. So now this band will shift up by V. So this barrier will be lowered by an amount V, right? So you can see this will become like this. Right. So you can see that the barrier has been lowered considerably here, depending on. Right. So if you apply voltage is equal to this potential difference created by this electric field here, then basically you can make the band flattening. Right. So you can see now that the electrons here can easily flow to the P side, right? And the holes here can easily flow to the N side. Okay, so another way to think about it is basically by applying this external voltage, we've applied an external electric field which is in the opposite direction to this intrinsic electric field setup. Okay, so when you add the two, the net electric field goes down. Okay, so there's a less of a barrier here for current flow. Right, so this intrinsic field you can see points from the N to P side, right? The direction of the electric field is from the N to the P side. Whereas, so when we apply this forward bias voltage, we are applying a positive voltage to P and negative voltage to N. So that's an electric field from P to N, which is opposite direction. Right, so that is what is lowering the barrier here. Okay, so you can see that basically what happens to this is, so if I look at the current flow as a function of the voltage applied, so at zero bias, I just this bare PN junction, there is no current, right? And as I increase this forward bias voltage, this barrier starts lowering, right? So at some point, basically this band becomes almost flat, and then the current starts really increasing fast. Right, and so basically, you know, this current after this turn on voltage or cut-in voltage typically scales exponentially. Right, so current scales exponentially with voltage here. Right, so these are basically diode characteristics in the forward bias region, you know, right? And this V on basically is roughly the barrier which was set up here, right? So for example, you know, for silicon, this is about like 0.7 volts. For 3,5 materials, typically this is also like around 1 volt or something. Okay. And so for our purposes, basically we want to make light sources, right? So basically the effect what we are interested in is, so in this depletion, what was the depletion region here, as these charge carriers are moving across, right, some of them might recombine, right, and emit light, right? So that's our purpose, that we want as many of these charge carriers, so electrons going in this direction, holes going in this direction, to recombine when they are here in the middle and emit light, right? And the more efficiently they do that, a better light source I have, right? So, for example, if you look at what is known as the luminescence, or the number of photons coming out from the device as a function of current, of course, that's a linear function of the current. Right? So, let's say a fraction of the charge carriers which are moving here recombine what is known as radiatively, which means they recombine while emitting a photon. Right? So, you can see as I increase the current, I am just increasing the number of charge carriers moving across. So basically, if the same fraction recombine, then my output goes up linear. Light output goes linearly with the current. Right. Or equivalently, if I plot the light output versus voltage, that will follow the current. Right. So that also. The luminescence curves that are basic characterization for any kind of optoelectronic device. Right? So IV curve, Li curve, LV curve. Okay, so if you just take this sort of most basic PN junction here, which is made of the same material, right? So we had the same material here, we just doped it P-type here, N-type here, right? And this interface was created. So this is known as what is known as a homo junction, right? Homo stands for one, so there is only one type of material with P and N. Okay. So you can see that this type of device probably is not very efficient, right? Because I mean these electrons are traveling fast across this region. Similarly, holes are like traveling fast across this region. So basically, the fraction of carriers which will recombine here to emit light probably will be very small, right? So, for example, there is some rate at which this radiative recombination happens. So there is some radiative lifetime, which is roughly telling you like how long the electron or the hole needs to spend here before they recombine. And if these electrons are zipping by fast before, they don't stay for that long here, then they will go out before they recombine. Right? So this type of homo junction device is typically not very efficient, right? Which means this slope will be very small with current. Right? So you're getting very few photons out compared to the number of electrons of hole passing by this decreasing per second. Okay, so the first type of devices which are made using these homo junctions, they were found to be not very efficient, right, and not capable of sort of providing the efficiencies and the powers that we need for sort of practical applications like communication systems, right? So then there is a modification done to this design, and basically what we do is we go from homo junction to what are known as double heterojunction to increase this radiative recombination efficiency. So basically what we want is these charge carriers, when they cross each other, to have the maximum probability of recombining and emitting a photon rather than doing anything else, like moving past each other or recombining in some other form, not emitting a photon. We want to avoid those scenarios, right? So basically, this double heterojunction was a very novel solution which basically enabled us to make very high efficiency optical sources, right? We convert a large fraction of our input electrical energy into optical output. And this is basically the design which is even used till nowadays for all the semiconductor lasers that we make nowadays. So this invention was given the Nobel Prize 2-3 decades back, maybe in the 90s. Anyway, so the idea is here is that, so of course we've lowered this barrier, right, to create a current. But what we also want to do is make these carriers spend some time here in the depletion region so that there is higher probability of radiative recombination, right? But if we just have this homojunction type of device, when we lower the barrier, they also spend less time, they just zip past flying at high speeds, right? So what you do is basically you create a barrier now here in the depletion region artificially by having a different material. Okay. So basically you try to trap these charge carriers here in the middle for some time so that they can recombine. Okay. So basically what is done is, so you have P and N, right? In between that, you sandwich what is known as an active layer, or active region. Okay, and basically the band gap, so this has a lower band gap compared to the P and N regions. Okay, so higher band gap for the P and N regions, so typically let's have the same material, but in the middle there is a layer of a different material which has a lower band gap. Okay, and so now there are two junctions here, right? In the homojunction there is only one junction here, but here you can see that there are two junctions, so that's why it's called double. It's a double junction, but also it's a hetero junction because now we have different materials. Okay, so that's why it's called double hetero junction. So now if I look at the, so now for example, if I apply a voltage and see how charge carriers are moving here. Okay, so this is a P region, N region, so they have large band gap. In the middle here is something with a lower band gap, right? And let's say again, so now we forward biased it such that so there's so this is P type, so EF let's say lies here in the valence band. Here EF lies in the conduction band, right? And the difference between these two is the potential applied, right? So this is the voltage, the forward bias voltage. So now let's see what happens, right? So so when we didn't have this active layer in the middle, basically what we saw was, okay, this barrier from N to P was lowered and the electrons will just flow like that, right? Similarly, holes here, right? They just flow like that. But now suddenly there is here a region where there's a band gap is lower than these surrounding regions. So when the electrons come here, they actually end up at a lower energy, right? And now they see some sort of barrier to go into the P region. Okay. Similarly, holes when they come here, they see some sort of barrier to go into the N region. Okay. So this kind of barrier which is created, you can see, is basically difference in the band gaps of this material versus this material, right? So now the electrons can't simply just rush through to the p region; they have to cross a barrier. So basically, they spend more time here, right? So it's sort of they're sitting in a well now. Similarly, the holes. Okay, so they spend more time here in the active region, right? And basically, what this does is that increases the probability of radiative recombination, right? So that more of them recombine to emit photon. Okay, and now notice that the wavelength is decided by the band gap of this active layer, right? So you can have p and n junctions of some other material, right? And that is not actually deciding the emission wavelength. You can decide the emission wavelength using this different material here in the middle, which is known as active, because that's where the recombination is happening and the light is being emitted. Okay, so basically this double heterojunction design increased the efficiency by many orders of magnitude. So for example, this active layer, you can have gallium arsenide, and this p and n regions, you can have some doping with aluminium. So what is known as AL gas, or aluminum gallium arsenide, right, with some fraction of gallium and aluminium. So as you increase the fraction of aluminium, the band gap increases. Okay, so depending on the amount of aluminium here, the band gap here will be larger compared to this region here with just gallium arsenide. Okay. So this again could be of the same. Okay. Or in the other material, indium phosphide, like the p and n regions could be indium phosphide, for example, and then the active region could be some combination of indium, gallium, arsenic phosphide. So this is like 1 minus x, 1 minus y. Okay, and so depending on the values of x and y here, the band gap can be lower than the indium phosphide. Okay, so basically this this sort of capability of changing the band gap by just controlling the atomic mole fraction was really helpful in making first of all these double heterojunction devices, which was much more efficient than the homology junction, and also now controlling the wavelength, right? So now by controlling the band gap of the active layer, so I can use the same substrate, for example, and grow different active layers in different regions of the chip and have like different wavelengths emitted, right? So it's a really versatile technology. And not only that, there is an additional benefit that sort of one got for free. So typically this active layer thickness is about, let's say 100 to 300 nanometer, in that range. Okay, so maximum maybe up to half a micron. Sometimes this can be made really small also, like less than 100, like tens of nanometer. Sometimes you go down to like 10 nanometer, for example. Okay, and so if you go down to sort of in the region of few nanometers, okay, so there is a technique known as molecular beam epitaxy by which you can grow actually atomic layers one at a time. Okay, so you can control the thickness down to like 1 nanometer, for example. So using that, you can make really thin devices. Okay, and then once this becomes really thin, right? If you now go down to 10 nanometers or below, now you know that basically the confinement becomes so large that now quantum effects for the electron start coming into play, right? So for example, this will be like a potential well here, and when it's so thin, basically you'll have discrete energy levels within this active layer, right? So now you can see that there will be only specific transitions which can happen, basically which is the allowed energy levels in this potential well. Okay, so those are known as quantum well structures or multiple quantum well structures, which are also made for some specific applications. But typically for telecom applications, we don't go for quantum well devices. So the thickness is typically, let's say, 100 nanometer or 200 nanometer, and yeah, just the basic double heterojunction devices has good enough performance. Right, so you can imagine this could be one way of controlling the wavelength very precisely, right? So we talked about coherent and incoherent sources, right? So for example, laser diodes, which are just sort of these PN junctions. If you just take this PN junction, pass a current through it, and look at the light coming out, that would be like a laser diode, right? This is a diode, and right, so that's why it's called a laser diode. So without any stabilization like that, for this kind of structure, you will get probably multiple frequencies coming out, right? And with the width of like few nanometers or up to 10 nanometers for laser diodes, right? But if you want truly single frequency with ultra narrow line width, like below megahertz or something, then one way to do that is, for example, make this kind of quantum well structure now where you have a discrete energy level. So that's a very well defined energy level here. Recall that just for the semiconductor, there was some spread in the energies here, right? There was some spread in the energies here, which is like roughly kVt. So when they recombine, right? So you can imagine that the emitted photon has a spread in energies, right? So that gives you like a spectral width. But now, if you have discrete energy levels, then basically the energy is very well defined of these recombining. So basically, the energy level difference is very well defined. So the wavelength or the frequency of the light emitted is also well defined. Okay, so that's one way of making sort of single frequency lasers. But we'll see that even with this wider, easier to make, cheaper active layers, we can do something externally, right? What we do is control the optical cavity. We make some optical cavity with this device here to control the spectrum or the line. Anyway, so yeah, so there was one extra effect that basically we got for free using this double heterojunction. Is because, so typically for most materials, the refractive index scales inversely with band gap. Okay, there could be some power here, but anyway, as the band gap goes up, the refractive index goes down. Okay, and this is true for almost any material, any solid state material you take. So here, basically, what happens, you can see in the middle there is a material with a smaller band gap, which means it has a higher refractive index than the surrounding P and N regions. So you can see that it's like a high index surrounded by low index. So that reminds you of a waveguide. Right? So if I look at the refractive index profile here, it will look something like this. So if I look at N versus position in the active region, there's a slightly larger refractive index compared to the P and N. Right? So again, one can solve the Maxwell's equation, the wave equation for this kind of structure, and you can see that there will be some kind of mode which is supported. Okay, so there is some guided mode. So this thing acts like a waveguide. Of course, this now confinement is only in one direction, right? Not in this direction, only in this direction. But still, you do get some waveguiding or confinement, so that basically your like light coming out is now like it's a nice optical mode which is coming out of the device. It's not like it's spreading light everywhere, right? So due to this, so imagine a thickness to this device into the board, then the light will travel sort of in this middle region, active region, like a mode. It's like a slab waveguide, right, made by that. So you get this additional waveguiding effect, which also enhances sort of your directional emission. Okay, so typically you can have like edge emitting or top emitting kind of devices. Okay, so like edge emitting would be, so your sort of P active layer and a sandwich like that, and then you have metallization on top and bottom, contacts top and bottom, then you pass current like this, and so the light comes out from the side like this. So the current is passed top to bottom, light comes out from the side like this. So these are known as edge emitting. Or you could have like surface emitting or top emitting, where so you cut out a portion from the top. Okay. So then you have these, then you have an active layer here in the middle. Okay, so this is like P, this is the active, then N. Okay, and these are metal contacts. So now your current is going like that, and then coming out here, right? And the light is emitted in the vertical direction out, right? And then you can also have like an optical fiber stuck right onto this opening. So the light emitter is directly coupled into the optical fiber. Okay. So typically, like you can stick this fiber using some epoxy glue or something directly to the device, and then directly couples into the fiber. So these would be like surface emitting. Okay. Yeah, and the point is that the dimensions of these these devices and so the active region and the mode that's emitted are typically matched to the fiber modes. Right? So typically recall the core size here of the single mode fiber is typically like a few microns in diameter, right? So the mode coming out of here is typically also similar size and can efficiently couple to the fiber. Okay, so let's just we just briefly mentioned these material systems, right? Aluminum gallium arsenide and then indium gallium arsenide phosphide. So let's look at them in just a little bit more detail to how we can control the wavelength of emission using different material combinations. Okay, so basically, so h nu or the photon energy, or I can write it in terms of wavelength, h by lambda is the band gap, right? So if I write Eg in electron volts, and then h and c are constants, you know that basically the wavelength of emission in micron I can just write as 1.24 divided by the band gap in electron volt. Okay. So there's this diagram that one can use to sort of select the material for the particular application depending on the wavelength you want. Okay. So one thing is so recall that what's happening is that we have P. So if you're growing this material, right? So for example, you grow the N material first, then the active layer, then the P material. And so if you're growing one on top of the other, their lattice constants have to be matched, right? So if you want to grow these materials in a crystalline form without any defects, right? Then basically you can see that there is a layer underneath which has some lattice constant, some interatomic spacing. And now I want to grow a new material. The only way I can do that without any defects or like dangling bonds or anything is if the lattice constant of this new material is the same as the material underneath. Okay, so these materials are grown by epitaxial growth, and you need to do what is known as lattice constant matching. Okay, so basically you need to ensure that your N active and P regions have the same lattice constant, right? You want them to have different band gap, but the lattice constant have to be the same. Okay, so fortunately, we can get this seemingly sort of contradictory requirement using some combinations of these 3-5 materials. Okay, so here on the y-axis is lattice constant in angstrom or 10 to the minus 10 meter, right? So that's the typical interatomic spacing scale, right? So like if you take silicon, for example, it's I think 5 point something angstrom. So typically for most solid state materials, that's sort of the range of the interatomic spacing. Okay, so for these material systems, right, like we talked about two of them, right? So by varying this x or the fraction of aluminum versus gallium, we can vary the band gap. So on the x-axis, we have band gap. Okay, and then from this relation, you can see the wavelength of emission is inversely related to the band gap. So if this is band gap in electron volt, then here on the same axis, I can sort of plot emission wavelength in micron, now going in the other direction because it's inverse. Okay, so you can see so 1.24 EV, which lies somewhere here, will be 1 micron. 0.62 EV, which somewhere here will be 2 micron. 2 EV here will be 0.62 micron. Okay, so this is like 1.5 here, 1.7 here. Okay, 1.3 will be somewhere here. Okay, so if you look at the telecom band of wavelengths, that's this range. Right. Okay, so basically now we can take different material combinations. So there's this one, and the other one is right. So here we have 1 degree of freedom x. Here we have 2 degrees of freedom x and y. So by changing those mole fractions x and y, we can basically move around this sort of parameter space. Okay. So, for example, if I take indium arsenide is somewhere here, that's indium arsenide, right? So indium arsenide, that's x equal to 1 and y equal to 1. Indium phosphide is somewhere here. I think this is indium phosphide. So that's x equal to 1, y equal to 0. Okay. Gallium arsenide is somewhere here. Okay. So this is gallium arsenide. And then aluminum arsenide is somewhere here. Okay, so gallium arsenide and aluminum arsenide have the same lattice constant. Okay, so this is a straight line here. And so any combination here of aluminum gallium arsenide with x between 0 and 1 will lie along this line, right? So this is gallium arsenide is x equal to 1, aluminum arsenide is x equal to 0, and any intermediate x will lie along this line. So you can see that they all have the same lattice constant, right? So I can grow algas on gallium arsenide or aluminum arsenide or gallium arsenide on algas, right? So it's easy to make any algas as a gas device for any range of wavelengths here. So you can see that the range of wavelengths here is sort of in the visible range. So gallium arsenide typically here it corresponds to like 850 nanometer emission wavelength. Okay, so the first optical transmitters that were made were from this material. So that's another reason, like the first generation of optical communication systems operated at like 850 nanometer, because that's what those were the sources that we had. Okay, but so that's the important point here, that the lattice constant here, if I change this x, does not change. Okay? So that's why we can build these double heterojunction devices. And then you have like gallium phosphide here, aluminum phosphide here. Okay, so you can really sort of, if you can vary these material combinations, you can really sort of span this map wherever you want. Just for comparison, we can see where the traditional materials are. So for example, here, silicon lies here, and germanium lies here. Okay, and so these points are connected by lines by continuous variations of these mole fractions. So for example, there's a line connecting here. And there's a line going like that up to what is known as aluminum tin. And there's a line like that. Then there's a line like that. Okay, and so for the modern day communication links, the sources we are interested in, again, so the wavelengths recall are in this range, sort of 1.2 to 1.7. So that we can span using this line, starting from indium phosphide up to here. Okay, so on this horizontal line, the lattice constant is the same, right? Which means we can grow these materials on top of each other, right? So, for example, we could have P and N with indium phosphide, and then the active layer somewhere here, depending on what emission wavelength we want. Right. So this goes all the way up to here. So this is basically indium gallium arsenide. Okay, with like 0.45 indium, 0.55 gallium arsenic. Okay. So basically, actually, there are simple expressions that you can use to design what material you need to grow for what particular wavelength you want. So for this line, right? So this is for the sort of near visible devices, shorter wavelength devices. So for the AL gas system here, the band gap depends on X using this simple function. Okay, so X here is between 0.37. So this aluminum 1 minus X, gallium X, arsenide. Okay. So that's sort of in this region here. Okay. So typically the good devices are made anywhere in this region here. Right. So this line within the shaded region here, that region corresponds to between X0 and 0.37. Okay. And the band gap has a simple relation with this mole fraction. Okay. So you can design so anywhere from 850 to somewhere around like 750 or 700 nanometer, between that range. Okay. Now, if you look at the modern telecom wavelengths here, so now so it's this in-gas P system. So there are two mole fractions X and Y. So here basically, if you want to lie along this horizontal line here, you have to match the lattice constant. So that gives me a relation between X and Y. Okay. So this horizontal line is for X by Y 0.45. So if this ratio between X and Y is not satisfied, then you won't be on this line. You'll be somewhere else here in this region or this region. Right? So you can think that, so the lattice constant also depends on X and Y, right? And basically for this horizontal line, the X and Y are related by this factor. Okay. So for if you pick a particular Y, you already determine X by this ratio. So instead of two variables here, there's only one independent variable after this lattice constant matching. So on this horizontal line here, from indium 0.45, gallium 0.55 arsenide to indium phosphide along that line, the band gap varies like this. Okay, so this now Y is going between 0 and 1, and X is going between 0 and 0.45. Okay, this is possible. Okay, so you can see that easily we can, depending on what wavelength we want, we can choose our X and Y and the materials that we need to grow, right? And the The growth technology is very well developed that you can really precisely control these x and y, and you can really precisely control the mode fraction to a very high degree. Anyway, so yeah, we'll stop here. We're already a few minutes over time. Any questions? Okay. We'll stop here and continue on Thursday. See the GOP students in the lab class now. Okay, take care. Bye. The question is it 1.35? Yeah, so this is 1.35. Yeah, I mean, all these expressions are given in your textbook, and don't worry if you don't, or I might have even made some mistake here, but all the expressions etc. are given in the textbook, the relevant sections that I post. But yeah, so you can see for this system, the band gap is slightly lower, right? Because we are talking about higher wavelengths. For the ALGAS system, the band gaps are higher because we are talking about lower wavelengths.